Okay, so next lecture is about, well, some facts on training. It's not about any algorithm, but let's say that if we hear some concepts, we should know what we are talking about. So we are going to talk a little bit about the training set, how the training evolves when you're using example and updating your parameters. What is overfitting and underfitting? We'll talk a little bit about regularization and hyperparameters, okay? So, well, sometimes when in supervised learning, we will have examples, and we will have, let's say, the examples are the X, and the ground truth is the Y in classification. So when we have a large amount of data, we have to split our training data in, let's say, in two sets. One is called the training set that you are going to use to update the parameters to get the good model. Okay, so most of the data in your training data that is labeled and it's supervised, in this case, it's going to be training data. And with this training data, you're going to use that learning algorithm, whatever your network and everything, and you will obtain a model. That means you will have a set of parameters, the W's and the biases and the hyperparameters, and this is what we're going to use later to see new examples. And in your training data, you usually leave some part of this data as a test data, okay? So you're going to see if your model is good to fit that data and to, for example, to classify correctly. Okay, once you have the model, then you try on your test data, you see whatever does your program, for example, classification, and then you say, okay, it works perfectly with test data or not, depends. One of the measures that you take had been explained by Santi. You can measure accuracy or recall and precision. These kind of quality parameters are the ones to be used to say if your algorithm has worked well. Okay. Okay. And just remember, one thing that is recommended is to shuffle the data, not to use maybe some examples that are one after the other are related. So you have to shuffle it, not to use similar data to train or to test. One thing is that some people are tempted to use test data for training, but you should never do that, otherwise your results are not good, okay? So don't do it. Well, let's say that I talk about X and Y when we have a set of data. One is your data, and the other are your labels. And your labels can be audio recorded fragments and the ground truth, or labels are words. Well, in images you may have this. You have images, and the output you may have classes like cats, dogs, and etc. Here you have some emails. Some emails. I read email here. Some examples about what is data and what are labels or outputs that you are willing to get. Okay. And as Santi mentioned, accuracy is one of the classic metrics. And why we are not using accuracy to, let's say I want to maximize the accuracy at the output, but why I'm not using this to train your data? Because it's not differentiable, so we cannot use it. So that's why we're going to those kind of functions like the one we've seen before, or this one, which, yes, they are differentiable. Okay, so that's very important. Some people now are defining metrics. There are some papers where you will see metrics that they are functions that are differentiable. But not necessarily that works better, okay? So this is the classical approach, to use some loss function and to use metrics which are classical and very well known. Okay, so this is what you will, when you see how is your your architecture or your network working, usually you also plot when training your loss with respect to the epochs. Okay, what is an epoch? An epoch is when you have updated your parameters using the whole set of training data. Okay, you do one pass with all the examples, and then you see, okay, how are my parameters? What is the loss I have obtained? Okay. Let's see here that we also have something called validation set. So again, you can split your training data mostly using what is training, but you leave a little some data for validation. This is, you are not using this data when training, but you are going to use it to see if it follows the same decrease of loss once you have run one epoch. If it goes parallel, it means that you're doing well. Okay. Let's say let's say you run through different epochs, but at one moment maybe you have been training your algorithm with that. Your validation data says, it starts creasing again. That means that here something happens. Maybe I can stop here. Maybe if I go farther, what happens, it's an overfitting. That means that your model, even if you train it more and more and more, you don't get better results. You go worse. We'll talk right now about this overfitting. Okay. So in any case, this is the typical way to see if you are doing well. And when you get here, you say, okay, you can measure, every time you can measure accuracy and see how it works, but here is the best you can get. Okay, what is the accuracy here? What is the loss that I get in my algorithm? And you measure your results, okay? Validation data also is used to set your hyperparameters that we'll talk later, okay? But you can use that to say, okay, yes, I'm updating the W's and the biases, but I also have a lot of hyperparameters. What should I do, okay? And, well, that's mainly how you monitor the training. Okay, overfitting, as I say, is when your validation loss starts to increase. That means that maybe you need more data. You have used a lot of data, and what you are doing with your data is not going well. So one way to avoid that would be, okay, you have to use more data. Maybe I'm going to start from the last line. Maybe you have so many parameters to update that your data is not enough, no? So one way is to put more data, but the other one is to reduce the complexity of your model, to adjust better to the data that you have. And then you have other things. Let's say that the other one that you have in image processing, I don't know in speech, but we call it data augmentation. That is to generate images that are not in your data set, but they are used to get more data. Imagine, for example, the images of faces. You have 10 faces. Why not to use a face which is a flipped version of one face? It's like another face, but you use your same data to generate more data. And you can do that depending on what. You can do rotation, image, you can do rotation, noise. You can do this, what is called data augmentation, to get more data, and this usually improves a little bit your results, okay? And finally, there are other ways to cope with overfitting, which is use some regularization. And there are like typical ones, this L2 norm that we have seen, okay, control the weights, do not put weights with a large value, so more or less all the values of the weights distribute, or use this dropout that I will explain you in a moment. Well, before that, just underfitting is like the opposite problem. That is you have a lot of data in maybe only few parameters. Okay, what happens there is that maybe you get that okay, your validation loss goes parallel to your training loss, but however it saturates to one value which the loss is still too very high. Okay, this is underfitting. And what you can do is just to, in this case, increase the model, the model complexity, use more layers, whatever you can do to do complex networks, and or in the case the opposite also is to decrease the regularization strength. Okay. In the case of, well, when you regularize your problem, you are trying to, and you have like a model space of all possible model parameters. You're trying to work in a model area where you can control more your let's say the error that it's produced, and this is called the regularization model space. And well, I have told you about this. You can do this L2 regularization, dropout. Something that I didn't work, none of us have mentioned yet, is transfer learning or pre-training. As I said before, in the backpropagation algorithm, I thought, okay, I have those weights. What do I do the first time I'm using weights? So the first time that I can do is, okay, I have a similar problem of someone that has used this network that works very well, and the first part of my network is exactly the same. Maybe I can use this weight initialization to transfer all these weights, that's transfer learning, and only, and I have a first update which is pretty nice already. Maybe I don't have it for the last layers, but this is a way to initialize, and also a way, let's call that, to control your model and to regularize. Okay, so if you heard about transfer learning, pre-training, that's what it means. It's to use other networks that have been initialized or used before that are similar to your problem and that can be transferred. Okay, as I talk about the weight decay, we can control also with this hyperparameter. How do I want to control the weights of the distributed weight of our model? That's the weight decay. Okay, the dropout, it's another form of regularization that what you do is, let's say you have your network with all your neurons, and what you decide is every time you do a forward pass, you decide with some probability that you are going to use or not that neuron. For example, if I say my probability is 50%, so every neuron has the probability of 50% to be used or not in that forward pass. So that makes that every neuron has more information, it's more robust against new examples, and so so let's say the network will converge slower, but in a more robust way. Okay, so every neuron knows more about the examples. If you use all of them, each one of them knows a little bit, and it's very the information that, let's say, it gathers is very narrow. In this way, we recreate what is called robust neurons. Okay. At the end, when you use that for testing, you use all of them, or sometimes not necessarily you are going to use them when trying to classify with this data. And finally, the famous hyperparameters. So our weights, our parameters are the W's and the biases, but there are many other hyperparameters that we have to control, and if these parameters are not well established, you're going to fail in training your network. Okay, and this is the first one is the learning rate, which is the update of the W's. Which weight are you going to use? The regularization constant, which is that weight that controls the the L2 norm, the number of epochs, the number of hidden layer, of course, that depends on the architecture, the nodes of each hidden layer, so your loss function, your activation function, there are many more of these, okay? And here maybe there are some heuristics for the beginner, okay? Why don't, I mean, if you go to somewhere, they say, okay, use 0.1 for your learning rate. And if this doesn't work, they divide by 3. And you have some, let's say, some heuristics that help you to start with deep learning, training a deep learning, okay? And, well, I think that's the end. Let's say, as you have seen training, there are many problems that you have to control: overfitting, underfitting. You use regularization to, in a way, to control your network, not to go to overfit or underfit. Usually, it's more likely that you have overfit. You have to train and to get a lot of number of parameters, and that obviously you learn a lot if the more you experiment. And that's why we also have here some teaching assistants that have experience on this kind of problems, and that can help you when training for the first time a deep network. Okay, and that's it. Any question? Okay. Okay. A question?
Many of these things that Elisa said, the toolkits that we are going to see afterwards, have a specific options, for instance, to choose one optimization or a specific method to change the learning rate and things like that are already implemented. So now we have a break. It's already finished. Yeah. 5 minutes.
Starti la festa?